So today onwards, for 3 classes, we'll discuss about Fourier transform and its implementation in numerical methods, through numerical methods, and some of the uses of Fourier transforms. Okay, so now the question is that what is Fourier transform? And I heard some conversations with you, some of you, and I realized that we need to have a little bit of primer on Fourier transform, not go into detail, but some primer on Fourier transform before we can go into the numerical techniques. And the numerical techniques which is of most use today is rather too complicated. One uses it like a black box, so that we will not go through in detail how it works, but we'll see how to use it. So today is mostly about discussing what is Fourier transform, where do we use it, why it is required, etc. Okay, so let us start asking you a question that I want to know what are the frequencies present in a electromagnetic radiation. Okay, so I have an electric field of the electromagnetic radiation, a magnetic field of the electromagnetic radiation. The radiation is coming to you, so you can measure the radiation. There are two questions here. One is that if I want to measure the electric field, for example, mostly you measure electric field because the amplitude of it is much higher than that of the magnetic field. Electric fields are easier to measure. All of our mobile devices measure the electric field or sends back the electric field. So if you have to measure the electric field, then what exactly do you measure? First question. Second question is that how do you know the frequency content of that signal? For example, when you are calling your friend, you are actually tuning into a very particular frequency. And in that frequency is what is called channel, through that you are communicating with your friend. So if you do not know the frequency content of that signal, it's not possible for you to communicate through a mobile phone. So the questions are, what exactly do we record? So when I say we, I mean our mobile devices or anything that can record something about the electric field of an electromagnetic wave. Both the batches have had some course on electromagnetic wave. PHY 102 has enough of electrodynamics as that you can answer this. The MSc batch, of course. Yeah, go ahead.
So the intensity of the wave.
Intensity of the wave. How is the intensity related to the electric field?
The amplitude of the electric field.
No, it's the square of the electric
Square of
Yeah, yes, sir. Square of
field.
the.
Right. So if you say square of the electric field, then you will lose some. If you just record the square of the electric field, you will lose the complete frequency information of the signal. So anybody from MSc, because you have had a more advanced electrodynamics course already. Let me, Vidhan.
Hello, sir. Yes, sir.
Yeah. So can you answer the first question?
Sir, I think each frequency of EM waves, like
How
angular
will
frequency.
you measure the frequency of the EM wave? How will you record it? How will you record the frequency of the EM wave? What is the device?
It is by the receiver of any mobile phone.
See, mobile phone has a lot of things inside, right?
Yes,
So
sir.
that is not the answer. What is the exact device which records it? You already have a course on this, and then this device was included in your course. Ria? Ria is
Sir?
sleeping. Yeah.
No, sir.
So what is it?
No idea, sir.
Vishal?
No. So is it like antenna connected to oscilloscope?
All right. So that's a good idea. So if you have an antenna, which is a dipole, so the device that records is an antenna. And what is the signal out of the antenna? Any idea? Vahal?
Hmm.
Okay. So let me cut in now. So what you record, the device out of the antenna, what it records is a voltage, and it can record how the voltage is changing with time. Okay, which is in if you know to calibrate your antenna, what you will then get is the electric field as a function of time. Okay. So this is not exactly what you will get, but approximately you will get electric field as a function of time. Exactly what you will get, we will discuss in the next class. Now that answers the first question, that this electric field as a function of time is what I record. Okay, how the electric field is changing with time. Intensity is the mod square of this. Remember that electric field as a function of time. So let's say that if I have a monochromatic radiation, and I am having a detector at a given place in space, I can call that space to be zero. I mean, that's my origin. So this electric field, I don't need to write down a special part for this electric field. But can anybody say what will be the form of this function if it is only a monochromatic radiation?
A e to the power minus I omega kx minus omega.
Oh, nice, nice. So let me write this as epsilon naught and then some cos 2 pi nu t. Electric fields are all real, so that's actually looks like this. But then for simplification of notations, we use complex numbers, because if you use complex numbers, they substitute for us a lot of trigonometric calculations. Trigonometric calculations, you need to remember a lot of formula. Complex number, you just need to remember how e to the power ix multiplies by e to the power iy, and that much only. So what you say is that this electric field is actually complex, and it's the real part of e to the power I 2 pi omega 2 pi nu t. Okay, and I will use a minus sign over here just to keep some convenience, uh, which will, I mean, you can use either plus or minus here, it doesn't matter. I will use minus because that will be in line with some books. All right. So this is all of us will agree that this is how the monochromatic signal electric field will look like. So you have to remember that you have to take the real part of the right hand side, where that's it. So that's the monochromatic signal. But what about a multichromatic signal, non-monochromatic signal? So how will a non-monochromatic signal look like? So what is the meaning of a non-monochromatic signal? It's basically, you can think of it as a collection of many, many monochromatic signals, right? The only thing is that each of these monochromatic signal, if I call that frequency of a particular monochromatic signal as 2 pi as nu, then that has an associated amplitude for that signal, which is epsilon nu, or the amplitude is actually epsilon nu times delta nu, such that then if you integrate over all nu, so it's integration now, then you get the electric field. Yeah, somebody was trying to say something.
Sir,
Yeah.
so like what's the sense of taking d mu as the integrating variable here?
What this d nu as the integrating variable here, right? So what you are saying is that each of these frequencies has a certain amount of amplitude. Okay, that amplitude is this much, epsilon nu times. So this epsilon is a little bit different from that, but give or take. So this epsilon nu times delta nu is the amplitude of the signal which is in between nu and nu plus delta nu. Okay. So now I ask you, so there are so many of different frequencies, each of them is contributing epsilon nu delta nu times e to the I 2 pi nu t. So the question is now, what will be the total electric field? So I'm just summing over all those different frequency contributions.
Okay, sir.
Okay. So it's not that you just take the integration, it is from a physical consideration, at least here. Okay. So now this has a name. So we'll call this can in general also be complex. So I put a tilde sign to denote that it's a complex number. So this relation is called a Fourier transform relation. Now, obviously, Fourier transform has nothing to do in general with electric fields or its frequencies, but this is an example where you come to it directly in physics. Now, there are details in this which I will not go through, and because this is not a Fourier transform course, so I mean in general, explicitly. So what you should have asked at this point is that I look at this integration and realize that the integration goes from minus infinity to plus infinity, and the integration is on frequency. What do you mean by negative frequencies? Right? So that I will leave for you to think about and explore on. So I'll not answer that question here. But one thing we have realized that we measure the electric field as a function of time, and then that can be written as the amplitude times e to the power I 2 pi nu t. This amplitude is different from different frequencies, and you have to just sum over those. But we have still not answered the second question, that how to know about the frequency content of the signal. Right? You have still do not know how to know about the frequency content of the signal. Now, before we do that, so let us carry this expression forward, the Fourier transform relation, into the next page, and then we'll do it from there. So Fourier transform relation. So E tilde as a function of t is minus infinity to plus infinity. Let me write d nu first, and then you have this epsilon nu e to the minus I 2 pi nu t. This can be written, or usually written, in a little different way. This is just probably how the engineers like it, and because of that we all, rest of us also follow it. See, nu, so you know that omega, which is the angular frequency, is 2 pi nu. So the exponent can be, instead of I 2 pi nu t, can be just I omega t. But then your d nu has to be d, if I want to change this to d omega, you get a 1 by 2 pi. So this is d omega. And now I also want to write the epsilon as a function of omega. So I use the same symbol here, though this is this can be a little different function. So I think that you understand that. So this is the epsilon, the value of the epsilon at the same frequency, mu. But I am denoting that as omega because just multiplying it by 2 pi. And then I have minus I omega t. This is how it is usually written. how do I get the frequency content? So remember that this is what I measure in our context. This is what I measure. So somehow I need to know what is this epsilon tilde omega, because that is the amplitude of different frequencies. So if this has only one frequency, what will be epsilon omega if there is only one frequency?
Epsilon naught.
Sir, if we
Anybody else
know
has to say
E
anything?
tilde t, then we can take the inverse Fourier transform to know about E tilde omega.
Right, so that will come to. But if you just think of from logical point of view, for a monochromatic signal of frequency, I will write frequency, this means angular frequency now. Frequency omega naught, what is epsilon tilde omega? Anybody?
So epsilon tilde of omega naught.
No. See, that is not correct, because you see, epsilon tilde omega is a function which is supposed to tell you what is the amplitude at all frequencies, right? It will not only tell you what is the amplitude at omega naught, but it should also tell you what is the amplitude at all other frequencies. Now, if it's a monochromatic signal, what is the amplitude at any other frequency? What is the amplitude? The monochromatic signal has amplitude at only one frequency, right? That's why it's a monochromatic signal.
Oh, so no, Dirac delta, right?
So
Function.
this is a Dirac delta function. Right? It's a Dirac
Yes, sir.
delta function. So now, so that we know that, okay. So if it is a monochromatic signal, I can guess that it will be a Dirac delta function. But what if it is in general? So somebody has already pointed out, I think Tanu has already pointed out, that there is a mathematical trick which is called inverse Fourier transform, which relates these two. And the inverse Fourier transform essentially tells you what is epsilon omega given E as a function of t. So I do almost the same integral, replacing E and epsilon from left and right. The integration is over t now because E is a function of t. The other thing that changes is the sign of the exponent. So that's my inverse Fourier transform relation. Okay, so now these two, once I know these two, we can proceed, because these are the things that we needed to start with. There are a few things I want to point out here. So you see that when I had here 2 pi nu t, then I did not have a factor of 2 pi outside. This is generally the case, that when I have the two variables, here I have two variables, so they are called Fourier conjugate variables. What are the Fourier conjugates here? The Fourier conjugates here are omega and t. So these are Fourier conjugate variables. So sometimes you will say that, somebody will say that omega is the real plane and t is the Fourier plane. So that means that you are talking about two Fourier conjugate variables, the functions defined in two variables, these two variables. Now, when in the exponent, you will see that there is a 2 pi coming with these variables, like 2 pi nu t. So in that case, in the first case, nu and t are the Fourier conjugate variables. Then you will not have any 1 by 2 pi factors outside. Okay. But when you don't have anything, so then you will have a 1 by 2 pi factor. So that is something to keep in mind. The other interesting thing to keep in mind is that in many books you will see that the definitions are different. Instead of 1 by 2 pi in the Fourier transform relation, you will see a 1 by root 2 pi sitting over there. That is done because if you do that definition, then in the inverse transform relation also you get a 1 by root 2 pi. And that's convenient because then your Fourier transform and the back Fourier transforms have the exact same scaling factor of 1 by root 2 pi. Okay, so let us use that here. So I will just use 1 by root 2 pi here because this is more convenient in all physics problems where we want both the relations look kind of symmetric. This is actually completely on you because where it will be required, can you guess where it will be required? This factor will be required, or this factor has to be exactly coined if you want to do what? Say I do a Fourier transform. This is transforming, the first relation is transforming E tilde, epsilon tilde to E, right? So I do a first time I do a Fourier transform, I convert epsilon tilde to E tilde. And then I do an inverse Fourier transform. So I convert that epsilon tilde. I should get back my E tilde without any factor. Right? Now there that extra factor of 1 by 2 pi or 1 by root 2 pi matters. And you can try and you can imagine here it's also itself because you are doing these two operations. What will matter is the multiplication of the two factors sitting in front of the integrals. So if I have 1 by root 2 pi in both cases, the total multiplication will be 1 by 2 pi, which will suffice. Whether you put the 1 by 2 pi in one or the other or 1 by root 2 pi in both, it doesn't matter. But this is just a matter of convenience if you use it, write it symmetrically. Okay, any questions so far? All right. So let me generalize now this. So let me make two statements here. So Fourier transforms can be written for arbitrary number of dimensions. Okay. So here the example that we took of the electric field, it has only one dimension, obviously. The time is only one dimension. But it can be written for arbitrary number of dimensions. Often in physics, we use the word conjugate variables, right? So for example, if I have x and y, I have the corresponding canonically conjugate momenta, which are px and py, right? In quantum mechanics, the wave functions written in the x space or the position space and the wave functions written in the momentum space are related by Fourier transform. So you know that quantum mechanics can run in all three spatial dimensions, which means that in that case, I can have a psi, the wave function, for the position space written in terms of x, y, and z. So it's a function of three variables. And I can do a Fourier transform, which is a 3D Fourier transform now, to go get the wave functions in terms of position space, px, py, and pz. So that will be a 3D Fourier transform. And obviously, I can also do back Fourier transform. Often, we'll see examples at the end of today's discussion that often in image processing, we use Fourier transform. An image lives in two-dimensional space. Right? Then, the other place where one uses Fourier transform a lot is solving partial differential equations. And there, the dimension can be anything depending on the dimensionality of your problem. So this is very important to realize that the Fourier transform relations can be written for any arbitrary number of dimensions. So let me write down a general form of Fourier transform, and just for the sake of to keep this point that okay. So the other thing. So let me just put the other point first, and then the other point is that we said that there are these two conjugate Fourier conjugate variables, and I gave you the example of the quantum mechanics where these variables are positions and momenta, right? Just now we looked at the variables as frequency and time. So there are many such Fourier conjugate variables. So there can be I'm writing pairs of, but if I have n dimensions, it will be pair to the power n if you wish. Okay, just to keep the second point home, let us write down something. Let's say that I have a function a, which is a function of the positions x. Okay, and I can write this down as 1 by root 2 pi So what is the conjugate of position variable in say in case of say electrodynamics again? You see, when we wrote down this e to the I omega t, it was introduced through electrodynamics. So instead of it, if I had to write e to the I here, so what will, sorry, ix here, what will be multiplying x?
So K.
K, right? The wave number, 2 pi by lambda. So this integration, so Fourier conjugate is between x and k. So this is I, sorry, kx. And I did not say that it is electric field, so let's still use minus here just for, okay. So that will be a nice Fourier transform relation, and then the inverse transform relation can be written like this. The other point is, again, it's a matter of convenience where we will use minus ikx and where we will use plus ikx. This is just one convenience or one convention that we are using. Okay. So k and x Fourier conjugates here. Can anybody say, for these two examples, here k and x, and the previous was omega and t, what is the relation between these two Fourier conjugates? Is there any striking relation between these two?
So the uncertainty relation, right?
No. See, uncertainty relation is a result of that relation, whatever I am trying to point out. So what are the dimensions of omega and
Sir,
t?
their product should be dimensionless.
Their products will be dimensionless. So dimension of p is inverse, or the dimension of omega is the inverse of the dimension of t. Here also k is 2 pi by lambda, if you remember. So lambda is length dimension, which is inverse of the, or x and k has the inverse dimensions. Okay. There is, yeah, go ahead.
So like similar relation can be found for E and T, right? Because they are Fourier conjugates.
E and T are not Fourier conjugates.
Okay.
See, even E and T.
Energy and time.
Energy and time. Okay. Energy and time is our Fourier conjugates, but when you go to quantum mechanics, the dimensions, I mean, you can say dimensionless, given that your dimension is measured in terms of h cross. Okay.
Yes, sir.
All right. So so there, I guess that this is all clear so far. So what we will do in next maybe 10-15 minutes is go through some properties of the Fourier transform, and I will stick to one dimension today for all the properties. Some of the properties we'll look at, some of the properties will I will ask you to prove by yourself from the definition itself, and so that will be the rest of the day. So any questions so far?
Sir, how to know if a given pair is Fourier conjugate or not?
Given okay, so it is not that a given pair variables you are given their Fourier conjugate, so you have to define the Fourier transforms between them. Okay. So see, this relation, it's not a relation that already exists and then you look at it. You are defining these relations. You are saying that if there is a function small a tilde k, then I will define a function a tilde x which is related this way. Then from a tilde x, I can also get a tilde small a tilde k by the inverse relation. It's not that they already exist and then you are trying to. Okay, so let's look at some of the properties. So properties. So the properties, so let me put here h as a function of x. I don't want h, I want a. So we had a as a function of x, right? A as a function of x and small a as a function of k. And I put tilde in both. If this is a real function, then a of minus k will be minus of a star of k. Okay. So if it is a real function, if I change in the a tilde, a of minus k, a tilde of minus k is exactly same as a star of k. So let me write it more clearly here. And we'll see later, this saves a lot of computation because you see, I can just, if it is a real function, I can just calculate the Fourier transform for k equals to 0 and greater than 0. And for all values at k less than 0, I can just use this relation. Okay. So I will ask you to see what is the relation if it is just imaginary. So what will be here? If it's an even function in the real space, so now I am using that terminology, then it is also an even function in the Fourier space. If it's a real and even, then here also it's a real and even. And then there are lot of combinations you can have it in between even and odd. And okay, I didn't write what will be if it is odd, so you should find out what will it be if it is odd. I'll show you one of them. I'll show you the first one, how to explicitly see that, and then the rest you should try to figure out. Now there are combinations of real / imaginary plus even / odd. So I can have real and even, real and odd, imaginary even, imaginary odd. So all these you should try to figure out what they are. Okay, so that's the homework. So let's see the first one here first. The first one is, I say that it's a real function, right? So I start with the Fourier transform relation, which is or let's start with the inverse Fourier transform relation. So I know that a tilde k is 1 by root 2 pi I'm just writing ax because it's a real function. Okay. So given this, let's calculate what is a tilde k star. Star means complex conjugate. So how do I take the complex conjugate of the right hand side? X is real, so it remains as x. Ax, I should take the complex conjugate of that, but we have already assumed that it's real. So this is just ax. And what is the complex conjugate of e to the ikx?
e power minus ikx.
Minus ikx, which let us write this way. I think that minus can be kept with anything. And then you immediately realize this is, what is this? What is this in the right hand side of the equals to sign? See, this is exactly same as the first relation, only k is replaced by minus k. So this should be a tilde of minus k. And that as simple as this you prove the first. Line here. Okay. Similarly, there are three more important things which I will write down. So the first is called the scale. Scaling. Scaling means that say I have, let me write down one of the scaling relations. Say I have this a tilde. Instead of at k, I know it at some alpha times k, where alpha is a constant. Okay. Here, what I will have is 1 by mod of alpha a tilde of x by alpha. So these two will be related by Fourier transform. The other is called shift. So if I have a tilde at k minus k naught instead of at k, so then what I will get here is, and multiplied by this.
Sir, can you explain scaling once again?
Yeah.
So this is similar to Laplace transform also, right?
This is yeah, this is similar to Laplace transform. Laplace transform in general is a broader area than Fourier transform, because Laplace transform, so when you write e to the ikx in Laplace transform, that can have, so this ik, instead of ikx I can have a complex number there. Ikx is a pure imaginary number. Okay, so if you take the imaginary part of the Laplace transform, that is the Fourier transform.
Yes, sir.
Okay, so let's, again, I will show only, as I said, I will show only one of these. So let's look at the shift theorem, and then the scale theorem you can try to prove by yourself. Or should I look at the scale theorem? So let's look at the scale theorem, because that will take less space and can finish it here. And so dk So if I can calculate the Fourier transform of this and show that it comes out to be whatever is in the left hand side, that is this one, so then it will be fine, right? And I will show it again, half of it. Let us assume here that alpha is greater than 0. So you should check what happens if alpha is less than 0. So what do I do? So what I do is I say that I do a change of variable. I go from k to something called say p, which is alpha k. So dk is dp by alpha, and I rewrite this integral in terms of p as dp a tilde p by alpha and here I write e to the I. K I will write as p by alpha and x I will write as alpha p. I'm sorry, x I will write as alpha x. Okay. So what you realize is the following. Just a second, sorry. Let me rewrite it a little bit because then it will be easier to do in one step. Okay, so let's rewrite it. 1 by root 2 pi minus infinity to plus infinity. dk I want to write as dp, so I get dp by dk is dp by alpha, so that 1 by alpha I write outside, so this is dp. A tilde k alpha is just a tilde p. And I want to write this because now the integration is on dp, on p, so I write this as p, ip, but p is, to write it as p, I need to have alpha into k. So if I have it p here, so I need to divide x by alpha, because then p by alpha becomes k and then kx, which is what it was there. But then you realize that whatever in the right hand side, whatever is the integral now is the Fourier transform of a tilde p, but the Fourier transform will give you capital A of x by alpha, because that is what is replacing x here. So this is definitely a tilde of x by alpha. All right.
Yes, sir.
Good. So let's move into something little bit more complicated and something more useful, which will be more useful, and we'll see examples of that while doing the numerical part. It's called the convolution theorem. So what is convolution theorem? So for this, let us first start by defining three functions. So one is, so let's choose the Fourier conjugates as x and k again. So I have ax and corresponding thing is ak. And I have b, bk, c, ck. And I guess that you now understand that one is the Fourier transform of the other, of small a and capital A, small b and capital B, small c and capital C. Now, there is an operation called convolution. This comes in physics more often than you think of. The master students has already seen it in action, and rest of us will see it in action shortly. So the convolution of, so what I am writing is that, so there is an operation which is called convolution. This operation is such that if you give it two functions, it will give you back one function, one new function. Okay. So here, if I give it two functions, a and B, it will give you back C. And I write this just a notational case. So this is the convolution. Okay. Now the question is that what is this operation? The operation is defined in the following way. And it can be shown that this is same as, so this integration is over all x. This can be shown that you can change the place of a and b as well. Okay, so this is the definition of convolution. So what happens if you look at what is happening here is that you have a function, say a tilde x, and you take the other function which is b tilde and change the position of the function over the other. So imagine that I have one function which is like this. So say this is a tilde x. And I have another function which is this, which rather looks like a Gaussian in this case, and we'll see in the next class why I draw it like that. And then what you do is you put this first function on top of the second function. So you put it here at a certain x, multiply the two functions, integrate it, and that is the value of c at that x. And then you go to the next x and you calculate c this way. Okay. Any question? So I've not talked about the theorem yet. So let's see what happens if I want to calculate ck. And that will be the last thing that we'll do. It will take 2-3 minutes to do the computation. So ck is obviously the Fourier transform of the of capital C of x, and I am not, because I will not be able to keep track of all the 1 by root 2 pi's, not keeping the, just for the sake of a little bit speed, not keeping the 1 by root 2 pi here. Okay. So I just write this as the integral of cx e to the power I kx dx. Okay. But then you will say that the C is by definition, so if you remember, C is the convolution of A and B, which is defined this way. So let us put that back here. So I have dx, and then okay, so let's have the e to the power ikx also, e to the ikx. Now c tilde x I can write as another integration between a and b, but now this integration variable has to be something other than x, otherwise it will confuse with the first one. So this is a x prime b x minus x prime. This is by the definition of convolution. Okay. Now what we'll do is we'll see that it is going to get quite complicated integral here shortly. So I put both the integrals first, then I write it to the ikx. Now I will do two more integrals where ax prime will be written in terms of its Fourier transform. So I have a dk of or say dk prime, it cannot be dk again because then I will confuse it with this k. So dk prime, so I'm just writing the Fourier transform of ax prime, and I forgot to put the tildes here, but that's all right. So this is a tilde k prime e to the power minus I k prime x prime. So I need to keep the variables, the track of the variables. So this is x prime, this is also x prime. Sorry, this is k prime and x prime. So I have e to the I k prime x prime. And then I have another integral. And then I will use another version of k here. This is with b tilde k double prime. Can you tell me what it will be to the power? Minus I, then what should sit there? So what is the x for this function?
So,
Yeah.
sir, can you explain that what is happening in the process of convolution? The two graphs that you had drawn.
Okay. Just a second. You have a class right now?
No, no.
So then wait for a little while. I will just finish this. See, what all I have done here is that for the people who are left, I will just keep on speaking for a little while. So what I have done is that I have kept the k integrals first and the k dependence also with them. And then I have the x integrals. You see that the only x dependences are in e to the power things, the exponential functions. So those are kept at the end because those integrations can be done together. And then there are two x integrations. One is on x, one is on x prime. They are kept separately and they are completely separate. Now you know that if I do this integral, so dx e to the ikx, and again modulo that factor of 1 by 2 pi is nothing but delta of k. That's one of the implementation of the delta function. So what I can write here is that a delta of k double prime minus k prime. So once I have this delta of k double prime minus k prime, I can do the k prime integration, and then the delta function k prime integration, what it does is that it changes wherever there is a k double prime, it changes it to k prime. So if I do two integration at once here, so what I will get is this. The k double prime integration also I have done, so that leaves me with, and this b k double prime becomes b tilde k prime. What am I left with is this thing, which is again another delta function, now on k minus k double prime, and that also is changed to k prime. Now you see that this is another delta function integration, and you immediately see that once you do the integration, what happens is that a tilde k prime will become ak and b tilde k prime will become bk, and that's the convolution theorem, which tells you that if a and b are related by convolution in one domain, in the Fourier domain they will be related by multiplication, and this is of a lot help in a lot of algorithms that we use using Fourier transform.